This is a station in our Introduction to the Gases lab called syringe. It's a really simple demonstration. What I have here is a sealed syringe. So there's some air inside of it, and there's a cap at the end that prevents the air from escaping or from new air coming in. All I'm going to do is, and I'll bet you have an intuitive sense of this, I'm going to push down on one side of the syringe. And as I do that, what happens to the volume? If I let up, you get more volume. I push down, you get less volume. Up, down. And then you could push hard enough to blow the cap off the syringe. That happens sometimes. But in doing that, you don't have a closed system anymore. So there's a pressure-volume relationship shown in this really simple exercise that I'd like you to write about in the lab report. Students, this station in our Introduction to the Gases lab is called vacuum pump. And what I've got here is a physical pump. It's like a motor that is going to draw air out of an enclosed container. Now, our enclosed container is this large glass jar that has a sealing bottom to it. And what's going to happen as the motor draws air out of that enclosed container is the pressure will go down inside. To demonstrate the effect of that, I have a balloon that's blown up about medium size. It's not a particularly high blown up balloon, but at least you can see the air in it. What I'm going to do is set the balloon on the bottom of this container. I'm going to lift the glass jar over the top of it. And there's a rubber gasket at the bottom so that there's an airtight seal. Then I'm going to take the hose that's connected to this motor and insert it to where there's an opening on the back side of this. And then I'm going to flip the motor on. And as I do this, I want you to watch in particular the size of this balloon and how it changes. Here goes. Notice the size of the balloon. It's getting larger, much larger. And eventually it's going to get to the size where, as we see here, it's actually blocking the opening where the air is being drawn out of the container. Now, I can release the pressure here. And you can hear the air getting sucked back into the container and the balloon taking on its original volume. Students, here's a station within our Introduction to the Gases lab called Candle on Water. It's a really interesting station because there's going to be a lot of things going on here. It's the explanation is a little complicated for this one. I've got a flask that's empty. I've got a candle, and the candle is sitting in a tray with water in it. What I'm going to do is light the candle. And then I'm going to cover the lit candle with an empty flask. Inside the flask is air, just normal air that you would find just in the room. I'm going to slowly cover this candle. And I want you to observe what happens, both to the candle itself and to the water inside. Notice that the water level inside the flask has gone up. It started at the very bottom, but then it went up. And at the same time, the flame of the candle went out. So I want you to think about that. What's going on here? And there are a few different ways you can tackle the explanation for this one. This is a station in our Introduction to the Gas Laws lab that's called crushing cans. What I've got is a standard pop can that is uncrushed. I put a little bit of water in it, just normal tap water. and it's sitting on a hot plate. I cranked up the hot plate. I can hear the water boiling inside the can, so I know that it's good and hot. Separately, I've got an ice bath, so a big beaker of water with some ice cubes in it. What I'm going to do is use these tongs to transfer the really, really hot can, and I'm going to quickly invert it so that the can's opening is underneath the surface of the cold beaker of water. In doing that, you're in effect sealing the can. Even though it was opened in order to drink whatever was in the can, when you invert it so that it's underwater again, the gas inside the can is sealed. And something dramatic happens here. This is kind of a fun one. I'm going to try to do this quickly. So I'm grabbing the can, and as the can was sealed, there was suddenly some crushing action on the can. Now you might say, Mr. Gaffey, did you do the crushing? No, I was not pinching hard enough at all to even make a dent in this can. That crushing action came from something else, and I want you to think about that as you write up the lab report. This is a station in our Introduction to the Gases lab called Balloons Underwater. What I've got is a hot water bath and a cold water bath and a rather small size balloon and a piece of string. I'm going to wrap the string around the balloon. And the string, in this case, is just used to gauge roughly the circumference of the balloon. So when I take a wrapped string around this balloon, and let's say I submerge it into the hot water first, and I'm going to kind of use a tool to help submerge the balloon, I noticed that the string, whoopsies, was stretching. Prior to falling off, it was stretching. Which means if the string was stretching, that means that the balloon circumference was getting bigger, which means that the balloon itself, the volume of gas inside the balloon, was also getting bigger. Okay, so there's a temperature relationship between the volume of the balloon and the temperature of the gas inside of it. Let's try the cold water bath now. Same thing. This time, I'm not going to burn my hands if I submerge them, so I'm not worried about that. And I notice that the balloon is shrinking to the point where the string is actually easily coming off. It's kind of like the balloon is losing weight and the belt around the waist is falling down. Wouldn't we all like that, huh? So we've got the volume of gas inside the balloon shrinking here, expanding here, shrinking in cold water, expanding in hot water. Students, this is called the pressure temperature apparatus. And I want to show you a sealed, rigid container that contains a gas, air, and it's attached to a pressure meter. Right now, the valve to the pressure meter and the system is open. And I know that because the handle to the valve is oriented parallel to it. But when I seal it like this, it's now closed. And right now, based on this pressure reading, our atmospheric pressure is about 17 psi. Let's use that as our reading. There is another unit for pressure called the bar that you can read, but let's use psi. So right now it's 17. That's normal room temperature, normal atmospheric pressure. Now what I'm going to do is submerge the sealed rigid container into both a hot water bath and a cold water bath. And I want to see how it changes from what we're reading right now, 17 psi. Let's start with the cold water bath. So here I've got a beaker with some water and some ice cubes floating in it. I'm going to submerge the container, and I want you to watch, if you can, the PSI meter. It's starting to go down. We started at 17. And as the temperature of the air inside the metal ball equilibrates, we're approaching 15. And if we let it sit for a little while, it might even get below 15. But we went from 17 to 15 PSI, just submerging in a cold water bath. Now, as you can see, take it out, the pressure should rise a little bit. Now we're at 16, it's going to keep going up. Next to the cold water bath, I have a hot water bath. So this one is sitting on a hot plate. It's the same size beaker, but this water has been heating up, and I'm going to submerge the rigid metal ball into that hot water. And I want you to watch the pressure meter. Ooh, it's going up, 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 up. Right at the moment, we're above 17. We're approaching 18 PSI. And if we let it sit for a while in the hot water, it should keep rising because the air inside the metal ball is going to start to acquire the temperature of its surroundings, which is the hot water bath. And without waiting a ton of time here, you can see that we're going up. We're currently at 18 PSI. So if you remember, room temperature was 17. The cold water bath, we got down to 15. The hot water bath, we're up at 18. And I could spend more time, but since we're only looking at a qualitative difference, it doesn't really matter as long as you're seeing the trend here. We don't need an exact number.